Beneath the surface, in murky water, a hidden trap waits for its target. The commercial fishing industry markets fluorocarbon lines with a specific promise: invisibility. Water is an active optical medium. As seen in this seabed view, the water's surface creates a refractive interface that causes objects to appear bent or shifted, a physical distortion that governs every visual interaction in this environment. Refractive index measures how light changes velocity entering a material. Pure water is 1.33. Nylon sits at 1.55. This difference causes light to reflect sharply, creating a glint. Fluorocarbon changes the math. At 1.42, it's closer to water's baseline, suppressing reflection and appearing dull. In low-light environments with complex backgrounds like aquatic vegetation, this proximity creates a successful illusion. The line vanishes into the patterns behind it. This state of invisibility is not a fixed property of the material. It is a fragile condition that depends on the absence of direct sunlight. When the sun reaches its peak, intense rays pierce downward through the water column. This trigger activates Snell's law, occurring the moment those rays strike the submerged polymer. When light impacts the line at a sharp angle, it no longer passes cleanly through the core. The change in density between the water and the line alters the light's velocity and trajectory upon impact. Under direct overhead sun, the line stops being a passive thread and begins to actively manipulate the light field around it. At a macro scale, the line is a three-dimensional polymer cylinder. This diagram illustrates total internal reflection. Light enters the material, hits the internal boundary at an angle, and becomes trapped inside. The line effectively becomes an unclad optical fiber, piping illumination downward as light bounces along the core. If the surface has even a microscopic nick or scratch, the reflection barrier is compromised. The light leaks out sideways into the surrounding darkness. The result is a failure of camouflage. The line suddenly flashes with a harsh neon glow. The same chemical engineering used to hide the line has turned it into a fiber-optic beacon. Understanding why this failure matters requires looking at the apex predators this material was designed to fool. Teleost fish possess specialized retinas packed with rods for low light and multiple cone types tuned to specific wavelengths. Their visual systems detect high-contrast anomalies and temporal flickering instantly, processing the aquatic world with a resolution far beyond human observers. The predator's eye snaps toward the glowing anomaly. To an evolved visual system, that light leak is a high-contrast alarm in a low-contrast environment. A single refractive mathematical trick cannot bypass millions of years of predatory visual evolution. The promise of total invisibility doesn't hold up in the wild. Real-world stealth is dictated by the background contrast, the angle of the sun, and the physical integrity of the line itself. Underwater camouflage is not a static property of a material, but a shifting interaction between physics, light, and the predator's eye.